Okay, let's jump into ground resistance testing. So the NEC defines a ground fault as an unintentional electrically conductive connection between a ungrounded conductor in an electrical circuit and the normally non-carrying conductors, meaning metallic enclosures, raceways, and things like that. So basically, it's between a ungrounded conductor, that would be an energized conductor, potentially energized conductor, and a non-current carrying conductor, which really means something that's conductive but not meant to carry current. So it's like enclosures or metallic raceways or the earth itself. So there's two types. There's two types of grounding. There's earth grounding, and this is an intentional connection from the circuit conductor, usually the neutral, to a ground electrode that's placed in the earth. So it'll carry straight current to earth ground. And then there's equipment grounding, and this is the grounding that ensures that operating equipment within a structure is properly grounded. Now you hope equipment grounding, you hope these never have to carry current to ground, whereas these grounds may have to in an unbalanced system. If you have a neutral that's connected to ground and the system's unbalanced, which is not uncommon, then the neutral will have to carry some amount of current. And then NEC kind of looks at these two in that light, right? So you don't expect these to carry current. These may sometimes be expected to carry current. Here's just a little illustration of a little stick man who's in the vicinity of some electrical equipment. And so here you have the non-current carrying conductors in that this might be a conduit or something like that, or a raceway. And so you'd have equipment grounding conductors basically for safety purposes. But then over here you'd have an earth grounding system because it's connecting the neutral of this Y-wound circuit here to earth ground. So two different types of grounds there. Here's a picture out of the NEC that shows, here's a metal raceway here. Here's a an enclosure. Here's your your ground for your enclosure with the bonding jumper, taking it to this terminal block, and then this carries any stray currents to ground, to the earth ground, typically a ground probe driven into the ground. And I think this is bonded to the metal raceway, and this is bonded to the enclosure, because this is called the supply side equipment bonding jumper. So it's coming from the supply side circuitry here. If there was any connection or any fault between any one of these current carrying conductors in this metal raceway, this would provide a path for it to ground. So the two grounding systems are required to be kept separate except for a connection or bond between them. The bond prevents differences in the potential from a possible flashover. From lightning strikes, you can actually have ground potential rise, which might bring the potential of this up, and you might cause a flashover inside your circuitry. So the primary purpose of the ground is for protection of life and prevention of damage to equipment. And the secondary purpose is to provide a path for dissipation of power, fault currents, and currents due to lightning strikes or static discharge. So why grounding? Well, if you don't have proper grounding, you increase the risk of equipment failure. It's a big cause of downtime. So the following are risks. The risk exposure without having an effective grounding system. You can have electric shock, instrumentation errors, harmonic distortion, power factor problems, and a host of other issues. If there isn't a dissipation path for fault currents to the earth through a properly designed grounding system, fault currents will find paths, not the ones you want them to find, and that will result in stray currents and also potentially ground potential rise. So a good grounding system provides safety, prevents damage, and improves system reliability.